Welcome back. In this lecture, we would discuss the topic on how to design a battery cell for a given rate capability. In general, if you know the charge stored in a battery and the discharge time of a battery, we can get to the current that can be obtained from a cell. If you also know the area of the separator, using this formula, you can also get to the current density that can be obtained from a battery cell. Before moving forward, let's introduce some terminologies. A deep cycle battery is one which is more or less discharged to its complete extent. Okay, so we can get more or less 100% capacity out of this battery. Such a battery is called deep cycle battery, if not to 100%, to a significant extent. As opposed to that, there are certain batteries, especially within the lead acid types, which are called SLI battery. This is used in a vehicle, in any transportation vehicle, not necessarily an electric vehicle. This is used for starting the car or starting the vehicle, for lighting application, and for ignition. Okay, so here the battery is not typically discharged to a significant extent, in contrast to a deep cycle battery. So what is the agenda in front of us? So the agenda is that we have an existing deep cycle battery. So this is the lead acid battery, going by the nominal cell voltage obtained from the battery with a particular capacity. It is typically discharged at a slow rate, so it gets discharged in about 10 hours. We will clarify this terminology later. The mass is this one, and there is an internal resistance, and the cycle life is this particular number. It can be charged and recharged, discharged and recharged 500 times if the state of charge is moved till 50% state of charge. Okay, so this is the existing specification of the battery. So we want to use the same chemistry, so the nominal voltage is the same, to design an SLI battery. Okay, so how do you modify this kind of a battery to an SLI battery, which with much lesser capacity, it's only 60 ampere hour. Okay, so we will try to use these specification to get to the desired SLI battery. How do we go about doing this? First, because the capacity is decreased from 1700 to 60, you may think that one way to do that is decrease the cross-sectional area of the battery. Okay, so this decreases the active mass. When that is done, because the cross-sectional area is decreased, the internal resistance of the SLI battery will be increased. An approximate increase can be computed in the following manner. You take the resistance, internal resistance of the existing battery, that is the deep cycle discharge battery, that is 0.4. You take its existing capacity, 1700. You take the desired capacity, this one, this 60. You can get to the what would be the resistance of the SLI battery. So the resistance increases corresponding to the decrease in the cross-sectional area. Also, because of the reduced capacity, you would think the active mass or the mass of the SLI battery is also decreased. An approximate calculation is provided here. The mass of the existing battery is 125. Scale it to the desired capacity. The mass obtained of for the SLI battery is 4.4 kgs. So this an additional terminology, rather a jargon, but it's an important jargon for you to understand. So this is called cold cranking amps. Okay, so there are three things here. Obviously, this has to do with current. Cold, because we want a battery to be operational at a very less temperature. This is true of, let's say, winter in the West, or even probably in Jammu and Kashmir. Probably you can get to a very low temperature. So the battery should be capable of operating at very low temperature, where the resistance would have increased significantly. And what you mean by cold cranking is, cold means at a very low temperature. Cranking means starting. Okay, you're operating the battery not for a long period of time, but only for a short burst. The burst can be about 30 seconds. Because it is cold, the voltage that can be obtained from a string of batteries, string of cells rather, cannot be less than 7.2. Okay, so what is the maximum current that can be obtained or that can be sustained for 30 seconds at minus 18 degrees centigrade without the voltage getting below 7.2? That is called cold cranking amps. Okay, this is an important design specification of a battery. Typically, a battery has 6 cells. So the typical voltage can be about 12. That's when we saw the nominal voltage in the previous slide of 2 volts. That is from a single cell. 6 times 2 volts gives you 12 volts from a battery, as opposed to 12 volts. Here, you cannot go below 7.2 volt. So we already know the resistance. We have computed from an approximate computation was provided in the previous slide, which is 11.3 milliohms. And if the overall battery voltage cannot be less than 7.2, from each cell, that is 7.2 divided by 6 is 1.2. The voltage from a particular cell cannot be less than 1.2. Okay, so the way to think about, once you have this, what is this useful information you can obtain? You substitute here. 1.2 is 2, that is nominal voltage, minus the ohmic drop. Okay, this is the dominant voltage loss because it is ohmically limited. Okay, so you know this. From this, you can obtain the cold cranking amps of the battery, okay, of this capacity. Okay, so just by using this resistance here, we can solve for I and get the cold cranking amps. However, this is what you obtain. Okay, that is not by the design specification. We need much higher cold cranking amps, which the desired cold cranking amps is about 560 amperes. So what do we need to do? What needs to be done is somehow decrease the resistance of a SLI battery. Okay, that is the only way to decrease the resistance. If you decrease the resistance, you can increase the CCA, that is the cold cranking amps of a battery. In order to do that, we can first get to the desired resistance. You plug in the desired CCA into the formula to obtain the desired internal resistance of an SLI battery. Solving for this, you can get the desired resistance to be 1.4 milliohm. We had already computed this, so the resistance has to be decreased. The one way to decrease the resistance is to increase the cell area by 8 times. Okay, so this would decrease the resistance by increasing the cross-sectional area. So all the desired specification has been achieved. Okay, so that is your capacity. We've accommodated that. This is for just cranking application. So you are discharging only for 30 seconds. CCA is about 560. Mass we have computed. Internal resistance we have computed corresponding to CCA. What is to be noticed is, because this is an SLI battery, you are only discharging to a limited extent. Okay, so if you discharge to a limited extent, just to 3%, that is only 97% is retained. So you're only discharging to a limited extent. The cycle life is much larger as opposed to cycle life here. Here, you are discharging to 50%. Based on that, you are getting the cycle life to be 500. That is, it can be charged and discharged 500 times. As opposed to that, if you discharge to a very limited extent, your cycle life increases. So as opposed to a deep discharge battery, the SLI battery construction is also different. Okay, so in a deep discharge battery, you have a thicker cell. So pairs of thick plates are utilized. Okay, as opposed to that, here the SLI battery, you have larger cross-sectional area, as well as you have very thin electrodes. Okay, this is the thin negative electrode, positive electrode separator, and so on. These are arranged in parallel. Okay, so there are 4 cells, 1, 2, 3, 4. They are arranged in parallel, and so on. Okay, so few things have to be understood. First, compared to a deep discharge cell, the thickness of the positive and negative electrode in a SLI battery is much lesser. The cross-sectional area is also correspondingly greater. Both these things contribute to lesser resistance, internal resistance of an SLI battery. So it is very important to understand the differences in cell construction. Okay, this aspect of manufacturing of the batteries, this is has to be appreciated to meet the design specification of a battery. So in the next brief lecture, we will look at certain aspects of cell construction. Okay, so this is very descriptive topic. We will not elaborate on this to a significant extent, but we will just talk about 2 major types of large-scale cell construction that is typically utilized. That will be taken up in the next lecture. Thank you.